The biggest shift this week is that reinforcement learning for AI is becoming more adaptive, more online, and much harder to break. Instead of treating prompts, thresholds, or rollouts as static objects, these systems now react to the policy in front of them, whether that policy is a reasoning model, a collider trigger, or an agent learning from live trajectories. That matters because the bottleneck is no longer just scale. It's keeping learning signals meaningful when the world or the model keeps moving. Here's what the new methods get right and where the old playbook starts to fail. Let's explore the first paper, LLM, as a tutor policy-aware prompt adaptation for non-verifiable RL. LLM as a tutor is a policy-aware RL framework for non-verifiable instruction following that uses one Qwen38B model as both examiner and generator to detect when a prompt is too easy for the current policy, and then append a single atomic constraint that makes the task harder without rewriting the original instruction. Trained with GRPO for 3 epochs on 4K wildchat prompts using Qwen 3, 1, 7B, thinking as the policy and evaluating on FollowBench, Advanced IF, and InfoBench, it achieves the strongest overall instruction following performance while preserving the seed distribution. On the reported benchmarks, it reaches 40.91 on FollowBench HSR, 62.28 on SSR, 15.07 on Advanced IF. Overall, 67.97 on Advanced IF Micro, 73.59 on InfoBench DRFR, and 51.96 average, beating policy-unaware baselines, prompt rewriting methods like eval-instruct, and the policy-adaptive EVA variant. The key technical insight is that rubric refinement alone cannot recover reward variance when a prompt saturates the policy, so the tutor performs pairwise rollout comparisons to trigger prompt augmentation only when quality is indistinguishable. Ablations show that the targeted append strategy matters. Always, random, and wrong fall to 42.13, 42.82, and 42.79 average, while the adaptive append design reaches 43.19 in the ablation setting. Analysis further shows constraint-added prompts rise from 8.1% to 40.5% as policy scale grows from 0 and 6B to 4B, confirming that adaptation tracks policy capability rather than a fixed schedule. Let's explore the second paper, Learning to Trigger Reinforcement Learning, at the Large Hadron Collider. This paper from the University of Chicago, the University of Michigan, and Fermilab reframes Large Hadron Collider trigger tuning as streaming reinforcement learning, where a policy updates a single threshold online to hold background rate inside a tight tolerance band while maximizing signal efficiency. Using CMS Run 283408 as the real data deployment target, the authors show that a basic DQN already improves over static menus, but critic-based and Lagrangian methods break under drift. GRPO and LGRPO often encounter zero feasible candidate groups, and CPO becomes effectively degenerate. Their main contribution is Group-Filtered Policy Optimization, or GFPO, with 2 variants. GFPO-F filters candidate threshold updates by smallest rate error, while GFPO-FR first keeps feasible candidates and then ranks them by signal utility. On Monte Carlo streams, GFPO-F raises in-band fraction to 1 on the HT trigger and 1 on the AD trigger, while GFPO-FR reaches 1 on HT and 0.979 on AD. On CMS data without fine-tuning, GFPO-FR achieves 0.95 on HT and 0.608 on AD, and GFPO-F reaches 0.99 on HT and 0.689 on AD. The paper also introduces a sequence-based state encoder with a GRU and a 22-feature observation vector, and shows the approach transfers beyond particle physics. On UNSW MB15, it preserves false alert rate control, and on NAB, it reaches 0.215 to 0.216 F1, beating an Oracle static threshold at 0.184. Let's explore the third paper, Single-Rollout Asynchronous Optimization for Agentic Reinforcement Learning. Single-Rollout Asynchronous Optimization (SAO) is a reinforcement learning method from Tsinghua University deployed in the Agentic RL pipeline for GLM 5.2 that targets the main failure mode of asynchronous LLM training, policy lag, and unstable off-policy updates. Instead of Grappo-style group sampling, SAO uses 1 rollout per prompt and trains immediately when a trajectory finishes, then stabilizes updates with direct double-sided token-level importance sampling strict clipping and masking, a faster critic schedule with k equals 2 value updates per policy update, frozen attention value model tuning, and a skip observation token level GAE for multi-turn agent traces. On reasoning benchmarks with Qwen 330B, A3B, SAO reaches 97.3 on AIM 2025, 74.8 on Beyond AIM, 88.3 on HMMT Nove 2025, and 74 on IMO Answer Bench, beating GRPO and remaining stable for around 1,000 training steps. On SWE Bench Verified, it improves from 27 with GRPO plus DIS to 29.8. The paper also shows that the single rollout design adapts better than running mean baselines in a simulated online learning task with shifting style rewards, where GLM 4-7 is used as the judge and SAO rapidly realigns after each preference shift. That's a wrap on today's AI paper highlights. Thanks for watching.